pleasure to introduce my good friend Tim Salcudean from the University of British Columbia. He has a pretty extensive background in the talk. He got his undergraduate and master's degree from McGill University and PhD from UC Berkeley. After that, in 1986, he joined the IBM Autonomous Geological Research Center. He was there for 3 years and helped pioneer magnetic levitation athletes, for example. And then after that, he joined the Department of Electrical and Computer Engineering at UBC, where he is a professor. He holds a Canada Research Chair, the C.A. Laszlo Chair in Biomedical Engineering. He spent a year at ONERA CERT in Toulouse, France, in the Aerospace Research Laboratory in 1996 to 1997, where he had a Killian Research Fellowship. He also spent 6 months during 2005 in the robotics group at CNRS in Grenoble. His current interests are medical robotics, for which he is extremely well known, and ultrasound image guidance, which he is also becoming very well known. He's, I think, one of the pioneers of a sort of a new field, elastography, which you'll hear about, I think, today, I hope. Medical simulation, virtual environments, and so forth. He's been a co-organizer of several symposia on haptic interfaces, served as technical senior editor for the IEEE Transactions on Robotics Information. He's a fellow of the Canadian Academy of Engineering and also a fellow of the IEEE. So, welcome, Tim.
Thank you very much. It's a pleasure to be here, as always. This is not very much a robotics talk, and I could have done a robotics talk, but this is very much mechatronics, and it's got a lot of flavor to it that you will be very familiar with. And I'm going to start by giving you an example of prostate brachytherapy as why you might want to use deformable models. And then I will give a tutorial introduction to elastography, then go on to my own work in the area with my colleague Rob Rowling, and discuss some results of the elasticity imaging of the prostate. Not that many guys over 50 in the audience, you would care about this, believe me, since 1 in 3 men over 50 do have some problem with that. And I will talk about a brachytherapy simulator, which encompasses a lot of my work over the past few years with an outstanding PhD student, Orchan Goksel. So here's the example of prostate brachytherapy. It's a cancer treatment of the prostate, which is carried out with the guidance of a endorectal ultrasound transducers. And you see here the acquisition of imaging, transversal imaging planes, each of these images looking like so. Once this volume study is carried out, there's a geometric model that's obtained for the prostate by segmenting the prostate in these images. Then a treatment plan is designed. And following the design of the treatment plan, a number of needles, somewhere between 20 and 30, are inserted into the prostate at the planned location, using long, flexible needles and a guiding template, which is rigidly attached to the ultrasound transducer, which originally did the volume study. Okay? So this is a fully geometric plan. Okay? The only thing that you acquire is a geometric model of the prostate. What does happen at the end is that you have a bunch of radioactive seeds, and over 6 months you slowly stop glowing, and the cancer is killed. It's a very successful treatment. The 5-year chemical relapse is, biochemical relapse is very low. However, when you look at inserting the needle into the prostate, the needle itself exerts a force onto the prostate, which actually moves, and you can see in the ultrasound images shown here to the side. In the first image, prior to the deformation, we see the bladder. In the second image, the bladder has almost disappeared. The prostate appears in the transverse plane that you're looking at. Okay, so as you insert the needle into the prostate, it will rotate and translate. And what happens is that you have a change in the target, which even if you have an absolutely perfectly needle, will still deflect. And if you do a finite element simulation, you will see that you have both a translation and rotation. The translation comes from the fact that the prostate is slightly better anchored at the pubic arch level than it is posterior to it. Okay? So why would we worry about deformable models? Well, it's a very interesting way of actually doing deformable registration. If we actually did have the accurate modeling parameters, then we could take a source shape and move it to a target shape based on a physical model, okay? Mechanical properties of tissues are actually constant across modalities. So if we do have an image of the prostate in, say, magnetic resonance elastography and one in ultrasound elastography, these images don't have much in common other than some mutual information, but they do have in common mechanical properties of tissue. We also want to correlate deformation properties to pathology. This is basically to replace the standard form of palpation that you go to see the doctor with something that is actually objective, that gives you a number, it gives you an image. And we will see that actually this can be used for surgical guidance as well. So how does this work? Here are two images of two tissue phantoms, you see that these tissue phantoms actually have some enclosures. There's a stiff enclosure, the round one here, and there is a stiff layer here. But the ultrasound images look exactly the same. If you, however, take two ultrasound images, one in uncompressed state and one in a compressed state of the same thing, the relative scatterers that produce the relative position of the scatterers that produce your image, okay, will actually be different. And you get what is called a strain image, which really nicely delineates the stiffer enclosures, okay? And there's been some pioneering work in this, sonoelasticity by Kevin Parker for Rochester, super bright guy, and by Jonathan Ophir from University of Texas at Houston. So here are the basic components of an elastography system. You look at your sample, you apply to it a mechanical excitation. Then you look at the image of the tissue as it deforms. Then you find the displacements of in that image. And then you solve an inverse problem, which essentially solves for the spatial distribution of elasticity parameters which are consistent with your measurements. Okay? The mechanical excitation, some of you will recognize this, this actuator as being the same thing that you find in the butterfly haptics device. It's the planar precursor of that is what you have in your disk drive. And basically you have a set of magnets, okay, and their iron return plates which act as an inertial mass which is pushed up and down by the current going through the coil, and that generates a vibration at the tip of the transducer. Okay, alternatively, you can take a vibrator, you can take your cell phone, put it on vibrate and put it on the body, and then you do your image, or you can take a needle and move the tip through a cannula, or you can take an RF ablator device and move it up and down. Alternatively, if you want to get into large forces, you can shake the bed and so on. There's another neat way of doing this is by using the transducer itself to generate a radiation, acoustic radiation force impulse by basically timing the signal sent by the array so that they arrive at the same time at a certain location that generates a push. That push generates a displacement. Then you can monitor the way the tissue returns from that displacement. You can also do this with MR, and we can use a voice coil in the magnetic in the scanner room. This is actually a 3 Tesla coil, and you actually don't need to have any magnets with your coil. You just generate a little torque by just putting the coil in the field. People also use piezoelectric actuators and and pneumatic transmission. We pioneered another system, which is a hydraulic transmission, which uses a water pipe to transmit the vibrations that you generate into a structural shaker from the console room into the MR room.
Question.
Yeah.
It would seem to me that what you get depends enormously on what frequency you're driving the system at.
Absolutely.
And it seems to me all of these methods are way too high a frequency to really get at tissue differences. It would seem to me that tissues at high frequencies all behave roughly the same because it's dominated by the fluid that they're in.
That's not true. And actually, you can get contrast in elasticity that has been shown in brain tissue, for example, all the way from 50 to 800 hertz. And the properties are consistent with linear viscoelastic models when you use small excitation, and you get actually power law, and everything is actually amazingly beautiful.
Is the picture the same at 50 and 200?
No, no. The elasticity can be the same across frequency, but you're jumping ahead. I'll show you. Yeah. Yeah. So here's an example of using a user's hand, okay, during a breast examination. This is using our software, which we license to ultrasonics, where you have a darker blue area, which is stiffer, and then the MD presses and then gets 2 images before and after compression, and from their comparison, they can make a judgment on how that lesion looks. You could have internal motion excitation. If you look at the carotid here, the carotid itself generates flashes of red, okay, and blue, which are basically changes in the strain, okay, adjacent to it. Okay, and so let's go a little bit through the modalities that to use. I'm not going to spend much time in MR. I'm going to spend mostly time in ultrasound. But because of the lack of ionizing radiation, really ultrasound and MR are the only 2 methods that have been used. People have showed this with CT, but with the controversy around radiation levels with CT, it's not a viable option. Displacement in ultrasounds can be found by using a correlation-based speckle tracking technique on the raw ultrasound echo data. So this is before this gets processed to generate a B-mode image. And basically, what we have is we look at a window in the RF line at a delayed time, and we slide that window, measuring the correlation. We find the peak, and therefore the displacement, fairly standard fare for people who do vision. We did this in real time. We're actually the first group to implement this on a commercial scanner. Ultrasonic licensed this software a few years back. You see here that you basically from applying deformation to the phantom, you start to see the internal structure that you don't see without that deformation. So a first approximation to the relative elasticity, okay, is the inverse of axial strain. So if you take 2 springs of different stiffnesses and you compress their series arrangement, the spring that is stiffer will compress less than the spring that is softer. So the inverse of the strain gives you roughly elasticity. You can also measure the direct shear wavefront of a wave that's introduced by the acoustic radiation force. And this is the technique adopted by Supersonic Imaging, a machine from France. The shear modulus can also obtain from harmonic excitation from the wave equation. or inversion using, from the wave equation, finite element methods in the static, harmonic, or Broadband approach. And we usually have a model fitting. So when you apply a motion to your tissue sample, you basically get a forward problem which finds displacements, okay, given the elasticity using a simulation of any flavor. The inverse viscoelasticity problem is to find the elasticity from the measured displacement, okay? And it's significantly harder. It's actually mostly an ill-posed or poorly conditioned inversion problem. What we've done, because I'm a control system engineer by background, is we treated this like a standard system frequency identification problem, the kind we used to work with Ralph Hollis at IBM, where you apply a broadband excitation to tissue, then you measure a sequence of images that provides you the strain or displacement as a function of time. Then you take tissue patches and you find their trajectories as a function of time, and then relative to a reference, which could be the motion or acceleration of the probe or velocity of it, you find the ratio of displacements of the tissue patches. And that ratio will give you a transfer function. And on that transfer function, you can put any norm you want, like an L2 or an L infinity norm, and get an image which is much, much more stable and nice than what you get from the strain image. Okay? So alternatively, we can use identify the specific of that transfer function using a Voigt model between stress and strain. Okay, and you can define not only an elasticity, but you can also define a time constant, okay, which is basically, you make this into 1 plus j omega tau. Okay, that gives you a time constant, eta over mu, which you can recover very simply from the phase of the transfer function. And even though you don't actually usually measure the stress, you can obtain, with a relative to a reference, you can obtain a relative change in tissue time constant. Here's what the images that this give you. Okay, we have here a phantom, okay, which has a gelatin background, the substrate, okay, and inside it we have a higher concentration gelatin, which gives you a higher stiffness. You have a contrast in stiffness from 7 kilopascals to 17 kilopascals. But these two have roughly the same relaxation time. Okay, you also have a piece of PVA sponge, okay, which has roughly the same stiffness as the other stiff enclosure, but it has a much higher time constant. Okay. So we have here the magnitude and phase of the transfer function images, and we have the coherence function, which, like the old HP signal analyzer, gives you a measure of how much of the transmitted energy to your sample appears linearly at the same frequencies. Okay. So from that, we have here the magnitude contrast, which gives you relative elasticity. And you see the two enclosures here, this one and this one. Or you can just look at the relaxation time, and because these two are about the same stiffness, you only see viscosity contrast. Okay? So this is pretty cool stuff. And you say, how can you get such amazing coherence function on a piece of gelatin? You know, it's basically you cook this to make jello. It's surprising, but this is even more surprising. This is actually data taken along a single A line of an ultrasound image, okay, which gives you roughly 1 over the compliance as a function of depth, okay? And this is actually an in vivo image, and we excite it here between about 0.5 hertz and 4.5 hertz. And look at the coherence function, okay, it's over 0.95, okay? This is living tissue with excitation of the level of 1 millimeter amplitude, okay? But strain images suffer from artifacts caused by boundary conditions. So we have here a simulated phantom with two enclosures, a stiffer elasticity and a different viscosity enclosures, okay? So if you look at, say, frequency of excitation at 5 hertz, and you look at the real part and the imaginary part of the strain, you'd expect to get something that correlates with elasticity and viscosity. But you have all sorts of artifacts, okay? These are from the boundary conditions that your strain does not take into consideration, and they change with the size of the exciter, okay? If you use a full plate to excite the sample, or if you use a part of the plate, the image is not the same, okay? So what we really want to do is we want to come up with a model for this, and we use a finite element model, okay? Which after discretization using Voigt's model for viscoelastic materials appears in a standard lumped form, an MBK system, in which M, B, and K correspond to the number of nodes that you have in your system, and at each node you have 3 displacement, Ux, Uy, and Uz. Okay? Now, when you do identify the parameters, and you find the parameters that are consistent with this model, okay, the estimated elasticity and estimated viscosity comes out to be perfect, okay? And as opposed to the strain, which actually has all sorts of artifacts. Well, it turns out that for those of you who've taken Chris's course, you'll remember that this when you do a control of a robot, you have the robot dynamics is linear in parameters. Okay, the same thing happens here. Dynamics here can be written in a linear in parameters form. You can see why I love elastography, because there's lots of stuff that you discover. Furthermore, if you write this in terms of the elasticity and viscosity of each of the elements in your discretization model, okay, you can write these in terms of a linear equation in the vector of elasticities and vector of viscosities, which form your parameters. And then as a recipe, what you can do is you look at the error between the measured displacements and the displacement generated by your model, and you minimize that. And furthermore, you can reformulate the problem as a QP or LP problem with constraints on E and eta. And even though the forces are unknown, there is a cool trick that you can do. You can define a region of interest, okay, which does not depend on your exciter. And in this region of interest, the force boundary conditions are 0. It turns out that if you have enough of these elements, even though these boundary conditions are 0, you can still invert your problem. And the reason why you can still invert your problem is that usually tissue density doesn't change, so you can assume M to be a constant. So M from the first equation, instead of appearing on the left-hand side, appears on the right-hand side with the appropriate density of water. And from that, you can recover parameters. And here is example of both viscosity and elasticity recovered on the top line in a PVC phantom with a hard cylindrical inclusion. And this is done at actually excitation of 20 hertz with a frame rate of 98 frames per second. And here we have an effective frame rate of 202 frames per second with a vibration at 90 hertz. How we get actually a frame rate of 202 hertz from an ultrasound machine which samples typically only at 30 hertz is itself the topic of 2 or 3 transaction papers, but I don't have the time to get into it. Here you have a breast phantom, breast biopsy phantom, in which you can see the internal enclosures, and you have basically numbers of, in terms of elasticity and viscosity in kilopascals and kilopascal seconds. Okay, can you do this in real time? Here's real-time inverse finite element problem solved on a PC with 8,000 parameters, okay, solved roughly once every 2 seconds. And this is without any GPU acceleration. Since this video was produced last August, we now have this GPU accelerated. We'll be able to do this at standard ultrasound machine rates of 10 to 30 hertz using that acceleration. There is a different type of inversion that we can do and for the harmonic case. This is based on the shear wave equation in frequency domain in a homogeneous medium. Okay, we have the wave equation, and there is a very simple equation which is a plane wave solution to this, which is basically corresponding to exponential of omega t minus kx, okay, where k is the wave number, except that now we have a plane wave and x is direction in space. Okay, so if you plug in ui equals ai exponential of jk times ni dot x, okay, with that value of k into the wave equation, okay, you get a solution. By superposition, okay, you can get a solution to the same equation by superposing all these planar waves. And what we can do is we can look at the sum of such traveling waves. That's why we call this a traveling wave expansion. Take a tissue region, and over that region, minimize over k and the weights of each of the plane waves that makes this expansion, the error between the observed and the predicted displacements. Okay, this actually turns out to be a linear problem in the parameters AIs, and it becomes a single parameter search over k. So we can do this in reasonably fast, compute this reasonably fast. And I'm showing here magnetic resonance images of an elasticity phantom. This is not designed for MRI imaging, so the contrast, the T2 contrast is not that great, but this, you have a number of enclosures. And these enclosures are designed by the manufacturer, okay, to be different stiffnesses. And our method basically gets very close to the manufacturer's specs, okay, in most instances. And we also have applied this to by sending harmonic waves transperineally to the prostate. And you see the waves that we generate. On the left, you have the T2 image. On the right, you have the Z, Y, X, and Y component of the waves. Okay. Note that even though, think of MRI at not having very high resolution, the maximum amplitude of the waves that we displace here is 2 microns. Okay. So this was before we actually perfected a bit our hydrospeaker actuator to get larger amplitude of waves. So here's the prostate image of a healthy volunteer, and you get basically an absolute map of the elasticity. You noted how the prostate in the region of interest is actually significantly stiffer than the surrounding region, and we will use that to segment it. Okay. So most of the approaches that I've described before have been primarily implemented on phantoms. In fact, our ultrasound elastography system has been used in a number of patients, and this is how this works. We acquire three-dimensional sagittal image of the prostate by using an endorectal transducer. This endorectal transducer has a sagittal imaging crystal, which we basically, as we rotate the transducer, from about minus 50 degrees, minus 45 to 50 degrees to plus 45, 50 degrees. While shaking it, we essentially obtain wave images through the prostate. The system is used by the radiation oncologist during prostate brachytherapy. You have here a slider which moves a carrier for the transducer. It's spring-loaded, so it's perfectly safe. You have a maximum force that you can apply, and the doctor can stop that whenever they want to do that. And this spring-loaded carrier rides on a cam, which you can adjust manually by moving the motor back and forth. As you move it closer, you see more of the angle of the variable angle cam, and that gives you transmitted waves through the prostate. We see here we have 9 patients that we acquired data for at the volume study. So this is before you actually go and have your treatment. It's at the time of the treatment plan. And then we have an intra-operative set of patients which we've done prior to their brachytherapy procedure. So this is a typical image that we get. The top row shows the prostate. The middle row shows the transfer function image of the prostate over between 0.5 and 5 or 0.5 and 10 hertz, depending on the case. And here we have the overall correlation, average correlation value that we used in computing these from the same RF data that generated the B mode. Okay, so you can see a significantly better contrast of the prostate in elasticity images than in B mode images. And you see that across patients. You see usually a beautiful rim, okay, of the prostate, which you don't really see in the ultrasound image. And we have actually quantified these images by looking at the contrast to noise ratio from the inside of the interior of the prostate to the outside, and again interior of the prostate to the outside in B mode images and elasticity images. And we get the contrast to noise ratio is significantly better in Vibro-elastography images. We also get that the edge strength, okay, so if you look at the gradients around the radial intensity maps, that edge strength and edge continuity from one radius to another are actually better for Vibro-elastography than they are for standard B mode imaging. Furthermore, if we segment the images both in MR, elastography, and B mode, it turns out that the images of the prostate are in fact closer to those that we get from MR, where you can see the prostate better, than those that you get from B mode images. So what we actually measure, there's a lot of evidence to say that what we see here is really the prostate edge. It is stiffer, it's what doctors palpate on for men over 50, and it's not an artifact. These contours, in fact, are good enough to use something like Chan VC active contour to automatically segment the prostate. Okay, so you basically start with a bounding volume, and you use a fairly vanilla version on Chan and VC active contours, and you basically get a reasonable hands-free segmentation of the prostate. And recently we have MICI submission where we've done the same with MR elastography images, okay, in which we use a combination of region-based and edge-based segmentation of the prostate in magnetic resonant images to basically get automatic segmentation of the prostate. Okay, I mentioned before that one attractive feature of actually knowing the elasticity parameters is that when you do something like deformable registration, this deformable registration is based on actual physical parameters and not some invented parameters, okay? So when you take two shapes that differ in shape, okay, A and B, what our approach is to look at the difference in the volumes and apply in the area which is intersecting, okay, shown in white, an increase in a fictitious pressure. Then on a meshed finite element method, we can compute the forces that derive from that pressure and take a surface which you presume your prostate to be okay, and one that you would like to register to as a target, and use those boundary forces together with the internal finite element model to bring those two shapes into coincidence. And here's what happens. These are the two shapes here in magnetic resonance imaging and in ultrasound. Okay. Here's one example of a registration from a group from Harvard, including Ron Kikinis and Claire Tempany, where you see very, very nice match of the surfaces. But in fact, this becomes at some point like pouring water into a bottle. You know, you will always take the shape that you want if you make it soft enough, okay? And what you see is the difference in the urethras is quite significant. Okay, in our algorithm, we actually use realistic values of the prostate elasticity, okay? And realistic value of the forces which generate equivalent forces which correspond roughly to what gravity forces would be on the prostate. And from that, we get also a similar match of the boundaries, but now when you look at the target registration error, you get significantly better values, okay? And we have done this with 10 patients. We have another 10 patients, the subject of the thesis of one of my students. Now, we can use these finite element models to create patient-specific models that we can use in simulators. Here's one such case where we take an MRI of a patient. We segment the prostate, bladder, the pubic bone, and so on, to generate a finite element model from which we fill it up with a tetrahedral mesh. Then we do the ultrasound acquisition that I've described to you that generate a map of the elasticity. We reconstruct a 3D volume. This 3D volume, we segment the prostate. We match to the prostate in MRI by using a registration process, and we end up with our model. This allows us to do needle tissue interaction simulations, the subject of the PhD thesis of Orchon Goxel, which can then interact with force feedback with a haptic device. And what we have is we have a model that shows us the transrectal ultrasound, the needle going into the prostate, and what the doctor would see when they guide the needle to the target in the ultrasound image. So that's the model view, and that's the actual ultrasound view. Okay. So you also have images of the needle and the deposited seeds, and we'll see this, how this is accomplished. Okay. So the first step in the process is that we take an ultrasound volume, okay, which is acquired with your sample and prostate in the undeformed case. Okay. So here's the ultrasound image of a sample that you may acquire while the sample is in the undeformed case. Okay, then you use finite element interpolation functions to compute the deformed ultrasound images, okay, of the same thing. Okay, so I don't know how many of you are used to seeing ultrasound images, but most people, including radiologists, cannot tell the difference between the real deformation and the simulated deformation using our techniques, because it's actually based on the acquired data. Okay. So this, with the ultrasound model of the prostate that we acquired the volume study time, and with the finite element model based on elastography, we can simulate how the prostate would deform. Okay, what's left to show is how do the needles look into the images, and how do the deposited brachytherapy seeds look in the images. And what we've done is we've used a robot that we developed for needle delivery to take images of the needles in water at various positions and orientations. Okay. And we embedded an ultrasound, a brachytherapy seed in a piece of gelatin, and we took the same type of images. Then we use tensor interpolation in 6DOF space to map those images back onto the ultrasound image. And here on the left is the simulated image. On the right is the real image. Again, very difficult to distinguish, okay, which is the original between these two. And we have a paper coming out in TMI this year on this. This is the work of another master's student. Here's the video of the simulator that encompasses all these features. You have the needle that you manipulate using either a phantom or a Novint device. We see here the Novint device. Okay. As you insert the needle, you will see its view both in the anatomical simulation on the left and in the synthesized ultrasound image on the right. Okay. You can see here where the needle appears inside the yellow circle. And you can see how the image is actually superimposed from the images of the needle acquired in water. The two are blended together. Okay. Then you can deposit seeds. Okay. You can press a button on the Novint. That will deposit the seeds, which you see as well in this image. And you also see them in the ultrasound image. They flicker in and out. They're very difficult to see, in fact, and they look exactly the way you see them. We can also do a simulation of the sagittal image of the ultrasound or the transverse, showing how the tissue deforms, okay, and the needle artifact view in the ultrasound image, okay, using the same superposition approach, okay.
What's the typical size of the seed?
It's the interior diameter of the needle is 0.6 millimeters. So it's tiny. Yeah, and it's about half a centimeter long. So if you want to simulate the template, an insertion exactly as you do it in the procedure, then you can actually simulate both the rotation of the needle, which the physicians use to find the flickering of the needle bevel in the ultrasound image. And basically, you can even reach behind the template the way they do it during surgery and push on the needle. The needle will deflect. Then the phantom will deflect relative to the template. That gives you actually the force that you apply on the needle. This can be used actually to do planning as well, not only the simulation, not only treatment. So if these are the targeted seed locations, you can fit a line through these targeted locations and insert a needle through those lines. And simulate using the finite element simulator where they will actually end up, okay? And they will not be exactly in the same place, okay? So what you do is you fit a best line through where these locations have been deformed, and you repeat this process a number of times, and this is a gradient-free fixed point iteration that converges typically in a few iterations, giving you the actual needle insertion trajectory. Okay, the simulations that we do require haptics rate. These are executed at typical few hundred hertz. You cannot do that if you have a 20,000 element finite element mesh. So what we're interested in doing, and I've given this problem to Orchun a number of years ago, is to optimize the mesh so actually you get a description of the object that you're looking at, which is fairly decent, but not using too many mesh elements. So what Orchun has done, he's started with the Delaunay triangulation using the one-ring neighborhoods of each one of the nodes, okay, as an energy function, which gives you one geometrically suitable mesh. And to that, he added an energy function which depends on the variance, the variability of the intensity of the image in each mesh element, okay? So the more the image changes in the element, the more you penalize that, the more you penalize this with an energy function. And then you combine these two, and then you minimize this iteratively by alternatively updating node positions and mesh connectivity. Okay, and here on the left, you see what you start with. Okay, here's a standard mesh. Okay, and you start with a single value approximation, and what you get is total garbage. You can barely make out what you have there. Okay, if you start to optimize the mesh by considering only a little bit the intensity that's covered by each of the mesh elements, the mesh, without changing its number of elements, okay, adjusts to the shape of to the target shape, okay? So this is really terrific work, because you start with a finite element simulation and you're saying, okay, what is it that I can compute at 200 hertz? I can do a, I don't know, 500 by 500 system at 200 hertz. So with that mesh size, what is it that, what's the best match that you can get to the actual image? Okay, so that's how we speed up the deformation. To speed up the needle simulation, this is very old work with Simon Di Maio. We use condensation, that is, we exploit the linearity of our finite element formulation to not look at all the nodes in the region, but only look at the nodes that are on the needle itself, okay? So by condensing the system using linearity, instead of having to solve for 1,000 nodes, you only have 10 nodes, and you have to map those to the 6 degrees of freedom that you have in your machine. So in general, I'm really excited about elastography as a mechatronic problem, and as a roboticist and a controls person, I find it's a beautiful problem with lots of parameters that actually gets real images of real patients. And it's amazing that you can do this imaging with standard MRI. Okay, it's amazing that you can actually image micron level waves going through the body with MRI and with ultrasound. You can use just strain to give you a flavor of what the elasticity is, but then you get artifacts. You can use model-based inversion to get more sophisticated images that have quite a few applications. Ongoing work is the correlation of our imaging method with cancer based on whole mount histopathology. We have 9 patients so far. Okay, we have 20 patients almost with elastography of breast cancer, and in fact, in every single case of targeted biopsy, we have correctly guessed when the biopsy should have taken place or shouldn't have taken place. So it's very promising in terms of reducing the number of biopsies for women that are tested for breast cancer. And we hope to use this for surgical guidance in a couple of surgery types and do a number of other projects. So this is the elastography related work. I still have maybe 5 to 7 minutes. I just wanted to give you a flavor of what we do with the Da Vinci system that we acquired at the beginning of January. We have 2 research robots with APIs that we purchased from Intuitive in December. And we're primarily concerned with the integration of ultrasound as a guidance tool for intraoperative procedures. And we want to do ultrasound both for its intrinsic use, and we also want to use ultrasound in order to bring in preoperative images into the OR. And we're looking at kidney surgery and prostate surgery for this. So here's work by Caitlin Schneider. We're looking at integrating ultrasound. The best state of the art from now comes from actually her own work at Hopkins, where you use a laparoscopic ultrasound to image the minimally invasive image the interior of your body during surgery. But lab ultrasound, standard lap ultrasound has only 4 degrees of freedom. It's awkward to manipulate. Every time you want to use the imaging, you have to pull out one Da Vinci instrument and put in another one. So here's the idea. Instead of doing that, what we will do is we will use a space between the trocar and the body to sneak in an ultrasound transducer. Okay, at the beginning of the operation, you have the cable going through. And then you have a transducer which is actually picked up by one of the Da Vinci tools, okay, and used like you would pick up a tool with your hands and put it down. So you just leave the ultrasound transducer somewhere in the body. You just go back and collect it every time you need it. You do not require a tool change because this is the most widely used instrument by the Da Vinci to grasp things and pick up and so on. So we have designed the probe to have an electromagnetic transducer in it. We will be able to place targets on it. It's a linear array of similar resolution as the arrays that I've shown you images by before. And we are getting this back at the end of April. So she'll be able to put that in her thesis. She has a presentation at the IPCAI conference coming in Munich in June. Okay, we can use these images to register ultrasound images, to CT images. Here's a flow phantom. This is a Doppler image of the flow. This shows the target registration error through the phantom, which is what we want to use to bring in preoperative CT into the OR. And here's some of the in vivo Doppler images around the kidney. They give you beautifully rendered images that we hope we can use for targeting. In radical prostatectomy, the surgery involves basically minimally invasive removal of the prostate, okay, while trying to leave the nerves intact, okay, for obvious reasons to all the guys in the audience. Basically what we'd like to do is we'd like to be able to visualize the vessels and the nerves that course right adjacent to the prostate. And for this, we will use the same endorectal ultrasound system that we use for brachytherapy, which has been robotized now, so it has 2 degrees of freedom, so the surgeon from the Da Vinci console can actually maneuver it. And unlike conventional ultrasound, we also have elastography. Here are images that show the stiffer enclosure in an elasticity phantom, commercial elasticity phantom for the prostate, versus the B-mode image, which shows nothing. And this is actually an image of the patient data. And this is work by Troy Adebar. He's going to be at CMU on Sunday. He was accepted in the PhD program, and he's looking at where to go. He also will present this at IPCAI at Munich in June. So this type of approach requires for us to somehow register the camera view with the ultrasound view. This is work by Mike Yip and Troy Adebar, 2 master students. So you look at the surface that you have on top of the prostate that you can see both with the camera and with the ultrasound. And what you want to do is you want to use this common surface to put fiducials on it that you can see both from the camera and from ultrasound in order to register these two. And we've done this with reasonably good registration accuracy. And once you register something like the MR image, which may show lesions, okay, you can actually track it intraoperatively by using a tracking system, which we now have working as part of Mike's thesis in collaboration with David Lowe. These are SIFT features that are tracked inside. This is a stereo view, HD view from the Da Vinci during surgery. You can actually feel you can see the heart motion, and you see basically in blue the features, the SIFT features that are being tracked with a little bit of temporal persistence in green, showing you where they've been. Okay, and this is running at about 1.5 seconds per frame in MATLAB, but we have another method which I can't talk about yet, which actually can do that 10 times faster. So when we do a C implementation, we'll have this running without GPU acceleration at a reasonable rate. So I'm going to wrap up here, and I'm open for questions. There are a lot of people who have been involved with this work. I have great collaborators, both clinical and the technical. Rob Rowling has been doing a lot of this stuff jointly with me. David Lowe, we just started last year on the feature tracking, and many students and postdoctoral fellows that have helped. Thank you.
Covered a lot of ground.
Yeah.
Questions? So,
Jing.
If you go back to the simulator, I was just curious, how exactly do you plan on using it clinically? Like, is it so that surgeons can actually train or plan the surgery ahead of time, or what's the purpose?
The answer is yes. We want to use this as a training tool. So right now, this procedure is taught to a resident by, the radiation oncologist, standing next to him or her and saying, yeah, push higher, maybe reach behind it. This needle is too high. You're not fully registered with the ultrasound transducer, all of that. So we'd like to eliminate that as a training system. Okay. But the beauty of this approach is that with a bit more work, and maybe not a bit, maybe a lot more work, you could actually make this patient-specific. You can acquire the volume study, you can acquire the elastography data at the same time. You have to do a little bit of segmentation of the bone. But then you can say, all right, I have John Smith that I'm doing on Thursday morning, and I'm worried that maybe his pubic bone is a bit lower than what I expect, and I may have to readjust the transducer. Can I check? And yes, you can actually go ahead and, based on the simulation, the volume study, you can practice on a specific patient with the specific image and physical properties or very close. So that's actually the big picture of where I hope this is going. So both general training and per procedure training. And furthermore, the treatment plan that they generate is does not include the deformation. So as you poke the needle in the prostate moves a bit. So when you actually look at the x-rays at the end of the procedure, all the seeds are spread a bit like this. And they're spread a bit like this instead of being perfectly parallel, because there is an anchor point which is a little bit less compliant anterior to the prostate near the pubic bone. So the prostate will deflect like this and like that, okay, when you insert the needle. So like this and like that, which gives you this flare of the needles in the X-ray images, is well known to radiation oncologists. So suppose you know now the deformation, you know how the prostate would move, you include that in the planning so that in fact there is less of this flare, then you're closer to the geometric ideal than you would normally do, and what that allows you to reduce the conservatism of your treatment, so you add less radiation to the bladder or rectum and the nerves. Yeah. Yes?
Could you share your comments for vibratory actuation versus comparing vibratory actuation with steady actuation?
So, so basically, there are three approaches to elastography. Okay, there's harmonic motion, quasi-static motion, and broadband excitation. We introduced broadband excitation to the field. Okay. In general, what happens, you can see the best by looking at the finite element model, given what I assume about your your background. So we're trying to invert this, okay? So you have, you know what omega is, okay? Let's say we know the force, it doesn't matter. What you want here is, if we know M, we want B and K, okay? So you have a number of parameters, okay? So basically, for each unknown parameter, you know from system identification, a linear system will require typically one spectral line for every two parameters, because you have the sine and the cosine that gives you each an equation you can solve for the two parameters. So basically here we have measurements at every node. So even though we have many, many parameters, we also have many, many measurements, okay? So typically you get one parameter per frequency. So we would need really two frequencies to get a good measurement of both, a good decoupled measurements of both elasticity and viscosity, okay, as a rule of thumb, okay? What happens is if you don't know the force, okay, then what we do is we look at the sub-region here. And in that sub-region, okay, all boundary forces are zero. All forces are zero, okay? But this is driven by taking the inertia function and replace the force for every node, okay, for which you don't have the force with the inertia function. So this is now a harmonic system, okay, driven by inertial forces, okay? So again, it's sufficient to have one spectral line per two parameters, but your problem conditioning will become much better if you use multiple frequencies, and in particular broadband excitation. Okay?
For broadband, is that random excitation?
Yeah, we pretty much duplicate HPDSA from vintage 1980s HPDSA in software. Yeah?
You mentioned at the end that you think that elastography images can be pretty easily added to existing ultrasound and MR.
Yeah. Yeah.
How do you foresee that actually coming into play? Is it a software mod that commercial systems will add, or is it?
So, you know, MR is very much like research. You have, for every MR imaging modality, people spend years developing software and looking what happens, and they modify diffusion MRI a little bit, they modify this, modify that. You know, an hour in the coil is not unusual for a patient to do something like diffusion contrast imaging and tensor imaging, diffusion tensor imaging. This adds right now 30 minutes. My student who's working with Ralph Sinkus now in France, they just have a result. They cut this time to half while improving the signal-to-noise ratio by having a clever sequence, pulse sequence in the MR. So MR, it's always researchy, okay? Ultrasound, what I've shown you is it's used in the clinic. We have an ultrasonics machine. Typically, we have 10 to 15 minutes per ultrasound examination for a woman before deciding whether you go and do or not do the biopsy. Our examination with change of probe, change of machine settings, and data acquisition of a million kinds, the whole thing is between 4 and 5 minutes. So we barely have to change standard protocol now to add elastography. Once you take that voice coil and you embed it in the transducer, so you just switch it on and off, you can do that as if you were to switch from B mode to Doppler, you switch from B mode to elastography. Yeah. And the reason why it was important to achieve this in real time is exactly that. So I don't know where I put that actually. Yeah, this is pretty much how the interface looked for the first 5 to 10 patients where we acquired the data. where you see the B mode and you see the elastic modulus, the loss modulus. You see the coherence function, which is mapped between 0.8 and 1. So, you know, it's not as bad as it looks. This is a very, very expanded range. Yeah. And as I said, this is once every 2 seconds without any CUDA, no multi-thread. I think we use multi-threaded tasks, but that's about it. Yeah. So, and in fact, it's getting to the point where the actual motion displacement takes as long to solve as the FEM.
More quick questions?
So these are all reconstructing 2D manifold surface in a 3D space. Is there anything to be gained from modeling these organs volumetrically?
Modeling them how?
Volumetrically, the full. I imagine that the stiffness of inside the organ is different.
So MR, it's all 3D.
Right, but you're reconstructing a 3D boundary.
And MR, we're not constructing a 2D boundary. We're reconstructing a full 3D volume. Okay, so when you look at the traveling wave expansion, for example, in MR, okay, this is over a volume. Okay, so you look at the XYZ component of the wave. Okay. And we're looking at the displacement, and then we're looking at what's the traveling wave expansion over the same region. Then we shift the region, repeat the whole thing again. Okay? Shift the region, repeat the whole thing again. This is very high level. We have a TMI paper coming out. In fact, the physics behind it is totally mind-blowing, to me at least, because what you have is using ultrasound, okay, to measure displacement. So how can that be? Ultrasound goes at 1540, displacement, you know, how can you use ultrasound to measure mechanical displacement? Well, turns out that you have various ways of propagating waves into tissue, and these waves travel at, depending on how they travel at vastly different speeds. Okay, so if you take Navier's equation and you split it in a standard Helmholtz decomposition, you get two decoupled equations, one a vector potential, scalar potential equation. And they correspond to one, which is the P wave or longitudinal transmission. This is fast. This is 1540 in water. Okay, and you have a second one, which is the shear. Okay, this is shear modulus, and this is less than 10 meters per second for tissue. Okay, so you basically, depending on the boundary conditions, in fact, you can have a transverse wave that travels at 1540, which is the first shock when you apply the impulse to tissue, followed by a slow wave, which goes around 10 meters per second. So you can repeat your echoes to actually follow the wave that you sent first. Okay, so the physics of it is actually quite beautiful, and we have a paper in. We have a paper in the Journal of the Acoustic Society of America discussing what happens with the transmission of waves in viscoelastic, in liquidy type solids, depending on what happens to the boundary conditions. You know, if you have a sample which is fully constrained, okay, then things move very fast through it. Okay, if the sample can bulge, then things move slow through it. Okay, so depending on the boundary condition, you can get vastly different excitation, and what you see is a fast wave that goes through tissue, followed by a slow wave, which you can then follow by repeating the fast wave. So it's truly the physics of this problem is amazing.
Yeah, it seems remarkable that you can extrapolate so much from these measurements.
Yeah, yeah.
So, I'm just getting on the
Chris.
One last question from Chris.
So, I'm interested in two applications where measuring sort of normal behavior. One is competing with fMRI and measuring blood flow in the brain.
Yeah.
And the other is measuring muscle activation or muscle force,
Yeah.
resolving what's happening with redundant muscles
Yeah.
during normal behavior. Is anybody using this to do that?
No, it's basically MRE is, I think there may be 1 or 2 papers on this. MRE is fairly new. Not only is it new, but there are some patenting issues happening around technology spun from Mayo. So other than GE, who licensed that, nobody really can sell an MRE system in the States. Okay, but we are in Canada, and we do have a Philips system. And the person who actually originally developed this has worked with us, so we do have such a system. So you could put an arm in the MRE, and you could actually image it as you say were to contract your muscle or work against the sinusoidal excitation to see how the waves travel through the body. You probably missed the part of the talk when I spoke about the MRE. You know, you basically have a system which uses a hydraulic transmission to transmit waves to the prostate, and these are kind of how the waves look through the prostate. That's the region of interest where you have them. And you know, it's easy to imagine how you would take the standard MR environment and you know, work your hand against an actuator and do the same thing. And in fact, there are much cheaper MRI systems, so you guys constantly apply for grants. This is a good one to go for. You know, you get a small MRI which is used for limb imaging. You know, people who have sports injury, they don't go through a full body coil MRI. It's much cheaper, like $400 versus $2,000 for the examination. And if you have the right pulse sequence, then you can do this. And unlike ultrasound machines, which are typically sold closed, like you have, you know, what you see is what you get. MR, you know, because it's always physicists who run those machines, you have all the access to change your pulse sequence whichever way you want. So in some sense, it's easier to do this on an MR machine than it is to do on an ultrasound machine, unless you buy a machine from Ultrasonics or B&K.
So I think we should quit at this point. Thank Tim.
Thank you.